Okay, Yihao, please.
Okay. Okay. So the paper I'm going to present today is called Poolingformer. It's a long document modeling with pooling attention, and the work is a collaboration between the University of Sichuan and Microsoft Research Asia. So let me introduce some background before getting into the main content of the paper. The transformer, this work is building based on the transformer. So it's an improvement. It's an improvement on the structure of transformer to take in longer documents, because previously the transformer can only take in like 512 tokens maximum for the input sequences, but for this work, it is able to take longer sentences, like thousands or a few thousand tokens. And let me introduce the self-attention before we get into the paper. So the self-attention in the transformer is to for example, if you have an input sentence as shown in the graph, the animal didn't cross the street because it was too tired, then the self-attention mechanism is used to let each word in this sentence to attend to every word in this sentence. For example, the eat, which is highlighted in the right column, and it will attend to each word in this sentence, and the model will give a weight to each word in this sentence as compared to it. And so that's by adopting the self-attention, the model is able to aggregate the context information of the sentence. And in detail, the attention mechanism is working as shown in this slide. You can see that we have three matrices, which is Q, K, and V. These three matrices are the linear projection of the original embedding of the sentence. For example, like, let me do some annotates. Okay. So, for example, we have a word.
Maybe we change another color, not in yellow, maybe in red or blue.
Okay.
So during Yihao is changing the colors, I just recap it. So basically, the attention mechanism has been very detailed introduced by Ruofan last week. But it's anyway, it's always good for us to recap what it really is. And also, I think it's very good that Yihao presents the specific formula here. So as Yihao has introduced the sentence, the animal crossed the street, and it will do whatever it is. And the what it actually refers to the animal instead of the street, right? So the self-attention mechanism is going to learn the relation between each token or each word in the sentence, so that it can be clearly infer the word it actually has a very strong relations with the word animal, which means that they are quite correlated. Okay, Yihao, please go on.
Okay. So, for example, the the matrix Q here is this is X is the linear projection of the embedding of X by using the weighting matrix, the WQ times X plus BQ. Yeah, so similarly for VKQ, it's all the different linear projections of the same embedding X. And here the WQ and BQ are the trainable weights of the model. So it will vary as the model during the training. So here we have the formula for the attention score is the dot product of QK and times the V. And we after that we take in the softmax to get a score that is within 0 and 1.
Well, here maybe I can have a small question for you. So Yifan, do you know what is the role played by this factor, this square root dk?
I think it's normalized. I check.
What if we do not have this factor? And Yihao, do you know the factor? Why? What if we just remove this factor of square root dk?
I'm not sure, but I guess maybe it might be if we don't apply this one, we may get the gradient exploding issue.
Basically, this the gradient disappearing is not a gradient exploring. So think about it. The softmax. Suppose the softmax we have. Suppose after we apply Q times K transpose, and we'll get two results. If one is 100, another one is 200, right? So if we apply softmax on these two values, and definitely it will turn into maybe 0.999 for this one, and this is for 0.001 for this. So in this case, there's no way to passing the gradients based on the first entry. So somehow we need to apply a normalization, just as Yufan mentioned, so that the softmax can, when we apply the softmax, the gradient despairing issues can be avoided.
Okay. So here, my first question is, what is the computational complexity of this attention mechanism?
Okay, so this is supposed to be a tough one. So when you're talking about computation complexity, maybe you can just specify the problem scale. And for example, the input length is n, right? The input length is n. And what is the other?
The input length is n. Yeah,
and so it means that maybe. So here, can you give a few options as the choices? For example, the first choice is ON. The second choice may be ON square, etc. Right? So maybe you can give a few choices for people to choose. And maybe someone can have a guess there.
Okay, so the first two choices, ON and ON square, and the third choice is ON log n. Maybe just
for one, right? Maybe I type here. The first one is ON. The second one, can you see I'm typing? No, right? Okay, so maybe I need to type something. So you can see it now?
Yeah.
Yeah, so there's three choices. And you can ask an arbitrary audience to answer this question. Pick one. We have 8 people for you to choose.
Maybe Yan Xiao. see.
Dr. Dr. Xiao. Any chance?
Yeah. So it's the complexity of all this part.
Yeah, maybe you can clarify. Yihao, you can clarify a little bit. So given the problem, given the input of n tokens, and we would like to calculate its self-attention, right?
Yeah.
And what is the complexity?
So the input length is, and when we do the this self-attention mechanism, what is the complexity? Actually, what is the complexity of this formula? Right.
The first one or the first and second one.
Yeah.
But I think the second one, I think the major complexity lies in the first equation, right?
Yeah.
And I think the second multi-headed attention does not have so large complexity as the first one.
Okay. Sorry, I'm not that sure. In my mind, I think it's the first choice.
The first choice.
Yeah, I'm not sure. Sorry.
Yeah. So here, yeah. So that is quite a tricky one. So maybe you
Can
can
I
answer
ask,
that.
it's the VKQ is
But
good?
I think Yihao haven't explained so well because for VKQ, it's somehow, I think this requires some background. I think Dr. Xiao is not so into these transformer stuff, and maybe we can let me check if I would have a choice.
I think the ON square.
ON square, right?
Yeah.
Because
It's just a two matrix multiply two matrix, and one matrix you can see the WIQ and is from D model multiply DK, and the WIK is D model multiply DK. So it's actually D model. It's actually the two matrix multiply. So it's n square.
I may have the same answer as you found, but my explanation is that for each tokens, we will have 3 VKQ. But the point is that maybe Yihao does not provide information very clearly, is that for each Q need to be interact with the K and D for every token, right? So that giving, suppose we have 3 tokens, T1, T2, and T3. And each token will derive the QKB, and the Q derived from T need to interact with T2 and T3. And similarly, the Q derived from T2 need to interact with T1 and T3. So by this means, the answer is supposed to be n squared.
Yeah, correct.
Can I ask why there's no D inside the complexity?
Because D is a constant, the dimension, D means the dimension. Do you mean this D?
Yeah. You can say it is.
But the matrix, like the QKV, they all have D.
Yeah.
Where?
can-
QK. Yeah, they will have D, but the D is constant. For example, giving a token, it will be turned into a vector of maybe K dimensional vector, right? And the K dimensional vector may, just as Yihao mentioned, need to apply some linear transformation into a D dimensional vector.
Yeah.
And that D dimension is supposed to be a constant.
Yeah, it's a constant, but when you take matrix multiplication, then you are multiplying this D-dimensional matrix. Then why
Yes.
not there will be a D inside the complexity?
I think the problem for the complexity is that for ON, if the complexity is n squares, 2n squares, or n squares over 2 over 3, they are the same. they all refer to the O n square. So that is basically the complexity.
So the only variable here is
notation, yeah.
I think this is a big O notation, right?
Yeah,
Yeah.
yeah.
I think the D will, if we consider the naive complexity, I think the D will be the constant of this n square, maybe n squared times D.
Okay, okay.
Okay, so I think we do not touch every details because for the discussion on these slides, it requires an expertise and background knowledge of the transformer. But I think Yihao raised a very good question. And here we just maybe remember the complexity to calculate the self-attention mechanism is O(n) squared. It means that once we enlarge the scales from the size of 512 into maybe 4,096, so the complexity will increase in a quadruple, not quadruple, in a squared way, right?
Oh, but
Yeah.
I checked one paper. Attention is all you need. And they say the complexity is n squared times d.
N squared times d. Based
So
on the
there-
notation, there's no
maybe they
difference
treat
between.
the D
Yeah,
a variable.
Yeah.
Yeah.
So the point is that if the d is a constant, there's no difference between O d times n squared and O n squared. Okay, so I think we can pass these slides because we still have another presentation there. Okay, so what do we need to memorize is that in order to have self-attention mechanisms, given the problem size, given the input size of n, and the complexity is n squared, O n squared. Okay, let's keep going on.
And this slide shows the overall structure of the transformer. So here we have the input sequence T1 to T4, and after we convert it into embeddings and we plus the positional embedding, then we feed it into the transformer encoder layer. I usually have 6 layers or 12 layers. And inside this layer, we have the self-attention mechanism and the feed-forward and some residual connection in this transformer encoder structure. And after the encoder, we have the encoded embeddings, and we feed it into our transformer decoder layer. And we also here is more like a regression model we feed in the tokens that we want to generate, and it will generate the next token. For example, we
by the way,
feed
the encoder output is actually one startup vector, right?
Yeah.
It is serious.
Sorry.
Is that the series? The encoder output is serious.
No, it's a sequence of tokens corresponding to this.
If it is a sequence of tokens, and how, because as I remember, if I still remember it correctly, and the decoder output, if we want to calculate the loss function of decoders, we need to generate the tokens one by one, right? So each time, for example, the first time, giving examples of raised by Ruofan in our last group meetings. Suppose the input is in Chinese and writing in Chinese, which means Zhang, and the output is supposed to be good morning, right? The good morning, and from the very beginning, we generate good first, and then we generate morning second. Right, and during the discussion, there's still a beam search algorithm to this end. In that case, and how suppose the encoder giving this architecture, the encoder suppose the input is somehow the input, the output of the encoder supposed to 3 tokens, three vectors, right? will be three vectors, supposed to be B1,
Yeah.
B2, and B3, right? And how
Yeah.
this B1, B2, B3 be used in the decoder?
In the decoder, it will be used as the if I remember correctly, it will be used as the key and value. So and the original input of the decoder will be used as the query.
Original input. Will you please repeat your last sentence again?
So you know, this in the decoder there is a module called encoder decoder attention, right?
Yeah, I understand this
Encoded.
layer. The layer basically is trying to try to extract the position relation. For example, the position 3 is actually related to position 1. Somehow it want to convey this kind of the ideas. But my question is that if it is provides the key and values of these vectors, and well, these vectors as one are input into the decoder. If it is key value, it means that giving V1, V2, V3, and for each VI, it will derive a KI and a VI, right? So, sorry, this V maybe in X instead, X1, X2, X3. And for each XI, it will derive the KI and the VI, right? And my question is that whether this XI will be used in the decoder.
XI, what do you mean by XI?
XI is output
which
of
one?
encoder. XI is output of encoder. Well, these output of encoders will be used directly in the decoder, or we just using the KI and VI derived from the XI.
Okay, we only use the KI and VI.
And
We
okay,
will
so my
not
so
actually
so
use
my
the
follow-up question is that anyway we need a start vector. We need a starting vector for the decoder, right?
Yeah.
And how we have the starting vector? Is that a CRS or something else? I just have a
The
random
starting vector. The starting vector is corresponding. So, for example, the input is T4, right? And get V1 to V4 here, and this is the starting vector of the decoder layer.
I think that. But the decoder generates the word one by one, right?
Yeah.
So in your graph, why this is T4 and T5, and this one.
I think
why
here
why here there's not the same length? Or what do you mean is that the starting vector is actually T1 here? Do you mean that?
Yeah. The CLS vector is, we can treat it as the T1 as the CLS vector.
So we're using these vectors or using these vectors?
We use the output of the encoder.
Okay, so basically we have output of encoder. Sorry, maybe I'm not that explainable here for discussion because I try to clarify Yihao's points. Since you fans do have the expertise, maybe you can correct us if my guess is wrong, because my memory kind of fades on these components. So Yihao, let me recap is that the point is that for the starting vectors, we actually using the CRS vector of the encoder output. Am I right?
Not only the CLS, it's all the output of encoder.
And
it's all the output.
And feeding to the decoder.
Yes.
And how can it be feeding to decoder?
So each token here will be generating the corresponding K and V vector.
Yeah.
Right?
I understand this K and V will be only be used as the encoder decoder attention. I do understand this point. But anyway, this decoder need to have something to start with, right? Basically, the Ki and the Vi are just the parameters. Just you serve as one layer in this in each decoder layer.
You mean the starter of the decoder?
Yeah.
During the regression. See?
during the generation.
regression. Generation. Okay.
Yeah.
So the first token to generate this output is the start of sentence token.
And how do we get these starting tokens?
It's defined in the vocabulary, and I think
this is quite weird. That means if it is defined in the vocabulary, it means that for each sentence, we just start with the same, exactly the same starting vector.
Yes.
Am I right?
Yes. Yes. When feeding into the decoder, for every generation, we start with the same vector by feeding the start of sentence token into the decoder and the encoder output into the decoder.
So if we want to derive a new sentence, it's totally based on this key. And for example, if we want to derive this first token or first word, and the dominant player is actually K1 and V1, right?
Yeah. It's actually the output of encoder.
Okay.
It's totally depend on the output of encoder for the first token of the decoder output.
Okay, I see.
So let me ask. So this is the first unit of the decoder. We can name as D1. So this input is the start token in the vocabulary. Yeah, and this input is the K1 and V1. Is it right? And the output the
we
first.
have the drawing,
Yeah.
And for D1, the K1 and the V1 is actually attached to D1. And so if we want to generate some things, basically the K1 and the V1 play the major role to generate the first token.
Okay, so for the next token, it's from this sign to here, and what's you will put another K2 and V2 to this D2, is it right?
Actually, the D1 token is attend to all the output tokens of encoder. It's not only K1, V1, it's all the output tokens from, for example, if the input is T1 to T4, then the output will be K1 to K4 and V1 to V4. Then each token of the decoder output is attending to all the tokens from K1 to K4 and V1 to V4.
Okay, so
sorry, I didn't get it. So the D1 here is basically, if I understand correctly, Ruofan's D1 here is just a position. It's just a position here, right? And what do you mean by this D1 is taking from all the token output, all the encoder output?
I understand the D1 is the input of the first token input of the decoder. So it's the start of sentence token.
Yeah, you're right. Basically, you can just remove the point D here. So basically, this is the first one, the first token here, and the major role played here is K1 and V1. Also, what do you mean by that? We still need to take the output of vectors. So let's make the terminology is very clear, and giving the encoder the final layer, output by the encoder is x1, x2 to x4, and each xi will derive the ki and the vi. All right. And when we are applying decoders, it starts with a unified empty token that's called a start, right? And this start will be input into the input layers and decoders. And here the only problem is that the self-attention, because this start is for arbitrary sentence, so the major role is ki and vi, and this xi will or will not be used in the decoder in the decoder part.
Mm.
Will or will not? Will not.
Will not.
Will not, right?
Will
So
not.
the only role played is K1 and V1. And then I would my follow-up question for you finds this line here. And for suppose this is token 1 and this token 2, right? And the input of token 2 supposed to be the output of token 1. All right. So here I'm suppose that we have the O1 here, right? And is this and will this line be used here? Hello, Yihao.
Yes.
Yeah. So the input of the position 2 is actually O1, right? Just as you mentioned.
Yeah. Yes, correct.
So our question actually is, besides because you can see that here this second neuron will get the information from the first neuron. Is it right?
Yeah.
Yeah. So what's the information get from the start? So besides this start token in vocabulary, what's this start? What's this? You can see that the 0. What's the 0 neuron information? It's not a K1 V1. We know KIVI will give information to all the decoder neurons, but we need to know what's the neuron 0 to the neuron 1.
I think neuron 0 does not provide any information to the position 1. The only information can provide is K1 V1. So that's my understanding.
But this is different because for the neuron 2, it has the information from neuron 1.
Yes.
But for neuron 1, you mean you just input the 0.
Yeah.
Like,
yeah, it's just placeholder. Yeah, that is what Yihao explained.
Okay.
Yeah, it just tell the decoder to start the sentence.
Yeah, but the start vocabulary is another input. I think the neural 0 should be something. Then
from the encoder.
Then he can.
That is also my suspicions. But so from the very beginning, I believe this would be a CRS. I think this is supposed to be a CRS of the sentence. But since Yihao mentioned this is the start tokens, that might also make sense. But maybe we need to have a second check after our discussion. Or maybe you
I can understand the start token because this is another input like the O1, but yeah, we should have another input compared to the D1 because the D2 have the input of D1 and the D1 need to have the input of D0.
I think is your D0 and the start are the same stuff or not?
No, the D0 is not different from the start token. The start token is actually an output like O1, O2, O3.
Yes.
But yeah.
But what's but O0 and O1 are supposed to be equivalent or
no. This is the neurons. The neuron 0 is different. The neuron 0 is like D0 and D1, D2 because before you start the D1, because like for the D2, you have the information from D1 because this is a line.
Here the O1, let's say the output of the first position is O1.
Yeah.
And the O1 will be served as the input of the, let's say this D2, okay?
Yeah.
And here the role played by
because
O1,
there's another information from the D1, because it's a LSTM or
it's a decoder. It's basically a decoder.
Yeah, it's
so maybe.
Yeah, so
this is not LSTM. If I understand correctly, this is not LSTM. So this may not. We may not. I have a question. Do we have this line? Because this is not LSTM. This is decoder. So we may not have this line.
No. This is LS. I think the decoder is a sequence model.
It is sequence model indeed, but the point is that everything here is not LSTM. It is a transformer architecture instead of the LSTM architecture.
But the transformer also has. You can see the before picture. You can move to the picture. I think
I think transformer is, for example, the transformer is proposed to replace LSTM. Right.
yeah,
So for LSTM, there's encoder decoder. You're right, definitely there. But here, after the paper, attention is all you need proposed. They want to use the transformer architecture to replace LSTM. So if I understand correctly, not like LSTM, there's no this information translation. There's no this point. If it is LSTM, definitely there's something here. There's something between D1 and D2. And here for transformers, and everything is a self-attention. So for any DI and DJ, they will be interrelated or calculated weights based on the transformer or based on the self-attention layer.
Yeah, actually this line, if you say it exists, then it exists in the self-attention. If you can see my mouse, the decoder layer here consists of 6 modules, and you can see the first module is self-attention. So there is a information exchange between the D1 and D2 in the self-attention module, but in the encoder decoder attention module, there is no this line exists.
Maybe I raise one last question on this slide, because the transformer definitely requires some background. So once we got the O1 and O2, and how do we calculate the bin search? Because we definitely need to have a joint probability between O1 and O2, right? So when we select O1, we're just using softmax, so that'll be very straightforward. But if we apply bin search, we need to calculate the probability on the joint. We need to calculate the joint probability between joint probability of O1 and O2. And how do we calculate the joint probability of O1 and O2?
I think in the beam search algorithm, they keep like a size of beam search. So they
I understand. I understand that we calculate, we keep the size. My point that so when we pick the O1, O1, and definitely we just select the softmax and then choose the top 3 one as the size. But what if we calculate the O1, O2? So for example, we have 3 candidates. The first candidate is good morning. The second sentence may be morning good, right? So there must be a probability designed by good morning and assigned to morning good. And how do we calculate the joint probability of good morning?
This one I need to check. I'm not sure.
Yuvan, do you know this point?
Pardon, please, I didn't.
My point is that for the bin search, in the bin search, how do you calculate the joint probability of O1 and O2?
You can apply chain rule.
So you multiply them.
Yeah, you multiply the probability of O1 times the probability of O2 given O1. So you will
just
have a big matrix. Yeah.
So here you just need to, for example, the probability of O1 is P01.
Yeah.
And for here, this is basically P02 giving O1.
Yeah. Yeah.
So the point is that we just need to multiply that.
Yeah.
Okay. Now that's very clear. Thanks all. I think we have enough discussions on these slides. Is there anyone have a question here? Okay, if no, let's keep going on. I understand our discussion is just a little bit messy, was a little bit messy just now, but let's clarify our points or the concepts with the following slides. Okay. Okay, thanks, Yihao. Oh, okay. There's a question here, right?
Yeah. So the second question here is why do we put positional? Why do we also put the positional encoding as our input, as an additional input of the original embedding of tokens?
So maybe that is also, you also need to pick up a student with such a background. Otherwise, some audience may not be that familiar. What is position encoding? Maybe you can first explain what is position encoding.
So positional encoding is is to assign each each word in the input sentence an index so that the model knows the relative position of each token in the sentence. So maybe Ruofan, can you answer this question?
Oh, okay. So I think firstly, because position matters in language. For example, if 早上好 becomes 好早上, then the meaning of the sentence completely change. So we need to add this positional encoding into our model. And second thing is that unlike the sequential model, attention does not incorporate this information itself. So we need to add it into it. Yeah.
Yeah, correct.
Okay, very good question, very good answer. Okay, let's proceed.
Okay. So here we come to the
Basically, so
the-
you may just mention this paper is actually just published in ICML this year, right?
Yeah. Okay. So let me introduce the approach that is proposed in the paper. So as we mentioned in the beginning of the presentation, this paper is aiming to is aiming to tackle the problem of long documents, because for the original transformer, it can only take 512 tokens as the input. So the maximum length of the input sentence is 512 tokens. But, in our real life, we may have many long documents. For example, our scientific papers is very long. It's certainly the length is larger than 500 tokens. So this paper proposed a two-level pooling mechanism so that it can the model can take in more than 500 tokens, and the complexity of calculating the attention is only O(n) square, so that given limited computation resources, we can also make the model running.
Oh, sorry, I missed your. Oh, please, Zhang, please.
Sorry to interrupt, but could you please explain more on what task this paper tries to solve?
Yeah,
Like-
so the problem, yeah, for the problem definition, yeah.
Okay, so the problem is that because for the original transformer, the longest document it can take in is 512 tokens.
The
And
transformer,
if, yeah, so if the document is longer than that, the transformer cannot handle it. Or this is why we set the limit to the 512 is because the complexity of calculating the attention is O(n) squared. So if the input sentence is too long, then it will.
Yeah, so that means for each attention layer, we need to have at least maybe about 250,000 calculation for each attention layer. And basically, if I remember correctly, for the transformer, it will have 6 encoder layers and 6 decoder layers. So the calculation will be even increased, right? That means for each sentence, there is such a calculation. For each sample, we need to calculate so many times. And given, suppose we have a database about maybe 100K sentence, and the calculation complexity and the calculation on overhead is quite large.
Okay.
Yeah, so for complexity of O(n) squared, it will cost too much computational resources to training the model when the input sentence is too long. So for this paper, it proposed approach so that the transformer can take in very long documents and the computational complexity of the model is only O, not O(n) square.
It's ONN and not ON square.
O(n), yeah, it's linear. It's linear,
Linear,
to the
it is a linear complexity. Okay.
yeah, it's linear to the length of input sentences. But it also depends on the other parameters.
Like slicing window size.
Yeah.
Maybe for each window size, it is suppose the window size is n, and for each window size, the attention is n squared. But since it is so I somehow got at the point is that so the self-attention is only applied inside the window size, and the different window will not build the self-attention connections between the window across the window. Am I right? So that might be the only way to make it linear. Otherwise, it's not possible.
Yeah.
Okay, you please go on.
So this paper has proposed an approach called the two levels Pooling model, and the first level is to apply a sliding window on the self-attention mechanism. So as you can see in this graph, the QI stands for the Q vector that is generated by the ith token of the input sentence, and K is also the QK and V is the QKV matrices, that is the linear projection of the original embedding. And you can see that the Q vector here only attends to K tokens that is within the sliding window. But the original transformer for this QI token will attend to all the K tokens. So here, when we apply a sliding window, it will only attend to tokens that in the window. Same after we apply the dot product between the Q and K, we get the attention score, which is showing here. And after we get the attention score, then we make a weighted sum of the V by using this attention score here to get the output of the token I, the output embedding of the token I. And in the second level, we use the output of token I to generate a different QKV vectors, and use these QKV vectors to again apply the similar mechanism, but here we apply a larger sliding window. And in the larger sliding window, we again apply a pooling module here to aggregate information from several K vectors in the sliding window, and from there we generate the attention score and make a weighted sum to get the final output of embedding here. So
I have a question here. So
okay.
So here, how if I understand it correctly, the length of, so here suppose we have n tokens here, right? And that means the k here, the number of ki, the number of ki is n. And here we need to generate zi, right? And the number of zi is still n.
Yeah.
Is still n. And how? And I didn't see it in a very clear way that how these window, the slicing windows apply to keep the dimensionality.
The I if it is from 1 to n, then the n is the length of input sentence. And so here for each I, we we go through this process. So we finally we get ZI from 1 to N.
Let me think about it. So let me repeat your process. So we will have slicing window, and this slicing window is the name is QI, right? And inside this sliding window, we apply the self-attention as what we do in transformer paper. And so, but for each sliding window, may I ask the sliding window will be overlapped? It means that the next sliding window maybe like this, right?
Yeah.
So in this way, for each token, it may have different embedding, right? So, but for example, suppose this is sliding window 1, and here suppose be sliding window S2, right? So there will have a let me do it here. This is sliding window 1, and suppose this is sliding window 2. Okay, so it means that for these two tokens, in these two are having overlapping. We have overlapping embeddings, right?
Yes.
We have overlapping embeddings, and how do they address these issues? So for example, suppose this is S1 and the second is S2. And both S1 and S2 will generate embeddings for maybe this is TK and a TK plus 1. And how do we address this issue?
Actually, their information might be overlapping, but the embedding is not overlapping because here for S1 we are using QI to generate these attentions for
this QI is for
S2.
By the way, this QI is for a window side, a sliding window. That means all the tokens in this sliding window share the same Q or share different Q.
What do you mean?
I mean that suppose we apply self-attention in one sliding window, every token in the window will derive a QI. Supposed to derive a QI, right? And my question just now is that whether this QI is shared inside the tokens of the same window or inside every token in the window will still have different Q.
So for a different window, we have different Q.
So that for each window, all the tokens share the same Q.
Yes. So for this same Q, we multiply, we use dot product to multiply it from Ki minus W1 to Ki plus W1 to get this attention score here.
So that means this Q is derived from the whole window, the tokens from the whole window. And then how they calculate the self-attention?
The self-attention is, the attention score is calculated by time, by dot product of QI, between QI and the tokens within the window, the K tokens within the window. So here QI is a vector and Ki minus W1 is a vector. We do the dot product, we get a number, which is the attention weight of QI versus Ki minus W1. So it's the attention score between token
okay. Let's
assume
that we got VI. Assuming that we got a VI, okay. So this VI will derive another Q hat. If I
but it's not called V. V is a is the vector that's derived from the
all right. So
maybe we call it Y. We can call it
I
Y.
I got it. But the point that's the different. You can see for different window will have different, may derive different K, right? Will derive the different K, the key embeddings for the same tokens. So just like TK and TK plus one. And how do they choose in further proceed?
How do they choose
Now, how do they further proceed?
to proceed?
Yeah, further proceed. For example, so so maybe another question is that for the tokens in different window, will they have the same value embedding?
When you say value embedding is,
Yeah,
you refer to this V?
Yeah, yeah.
Yeah, they have the same value embedding.
So every token will have this, even the token in different, suppose given a token which resides into the overlapping part of the two-sided window, but they will still share the same embedding, right? They will still have the same embedding. They will not
Yeah,
have the different embedding.
Okay, let me draw. Actually, this here we also have a column which is the Q. So here is from Q1 to Qn. Here is K1 to Kn and V1 to Vn. And for each Qi, it will generate a sliding window which is centered at Ki and use this Qi to multiply each token within the sliding window of K matrix, which is here. So we generate this attention score and use this attention score to make a weighted sum of V, which is also within the,
So
yeah.
so the point is quite simple. So just like transformers, it's now only apply the query on a sub range,
Yeah.
right? And that's all.
Yes.
Okay, so
Yes.
so the process is just the same. I think it's sorry, my source is too complicated. So it's not that complicated. So basically just control the range when applying the query, right?
Yes. Yes.
Okay.
And on the second level, it's applied the pooling to make, because it applies a larger window and it use pooling to aggregate the information together to minimize the computation.
Let me think about it. You have the pooling. So which two tokens? Can you mark the range to apply pooling?
Yeah, actually this one is the range to apply pooling. So it has a kernel size and it has a stride size, which can be defined in the model, and it will aggregate the information within the kernel size to generate this pooling vector. So if we use a mean pooling, then we calculate the mean of this K tokens and generate one new K token and use this Q to times this new K token to generate the attention score for this K. Yeah, so in this way we have
okay, so the point is that several tokens will share the same in the same value embedding or the same key embedding.
Yeah. Here a value and key is all pulling together.
So I think there's supposed to be no overlapping between the pooling, right? So suppose the window size is n, and suppose the pooling size, suppose we want to have the 3 pooling, generate 3 pooling. The pooling size is 3. We'll just have n over 3, right? The pooling will not overlapping.
Not necessary, because it also has a stride size, stride number.
If there's stride number, how they share? Because suppose we have stride here, the next time I stride here, and how these embeddings will be calculated?
It's shared. So when we calculate this one, then it's used, and when we calculate the second one, it's also used.
But in this case, if we have the pooling, the number of tokens has been reduced, right?
Yeah.
Okay.
Yeah.
Okay. Oh, okay. I got it. So basically, it was trying to derive a large pooling, a large window size, and once the window size is increased, the complexity will also be increased. So they just using pooling to reduce the complexity. That's all.
Yes. Yes.
Okay. Got
Correct.
it. Okay. Okay. Sorry for I kind of slow to accept these slides, but I think Yihao is quite clear. So is there anyone have questions on this slide?
Why we need enlarge the QI in the second level? I mean the first. Sorry, maybe.
Yeah, so I think these are good questions, and maybe I myself will try to answer these. The point is that since the token, the sentence is very long, so it depends on, so here giving one tokens, it may have relations with many other positions. But if we control or limit the sub-range, these tokens can only see within this sub-range. So in this way, they have to sacrifice or make the trade-off. So they control the precision, they try to sacrifice the precision, and the sacrifice is made by the pooling. Once they make such a sacrifice, they can see in a larger space or in a larger range. So that means for each tokens, despite they cannot see every token in a sentence, but they have the potential to see in a larger range. So that is my understanding. So the larger range you want to see, the more sacrifice we need to apply on the precision.
And
Yeah.
here, the second level, you double the size, basically double the size of the window. And
Yes.
how about if it's in the third level, would it like triple the size?
Oh,
Or
it is. I think it's also possible. I think it's also possible.
okay. Is it like somehow like the beams no,
It's not being. I think it's not being. It's not being. And I think that's the way to calculate the self-attention. So that means the only problem is that when we calculate self-attention with a problem scale of n, and when n increase, the complexity will increase in a squared way, in a squared way. So here we want to reduce the increase of size, maybe in such a linear way, right? So that is the idea, and they apply these by sacrifice some of precision. And I believe that in the experiment point of view, such a sacrifice is supposed to be lucrative. That means they will not lose the precision too much, but anyway, they still have they allow to they can support a much longer sentence based on such an approach.
Okay, can I ask what's the relation between the first level and the second level? I mean, I'm not that clear. When the first level will be used first and then use the second level, yeah.
Yeah, I think you're right. The first level, the output of the first level is the input of the second level.
Yes.
do they share the same weight or they are different?
They're different. I suppose they'll be different.
Okay.
Yeah. Actually, the paper tried different settings. I will illustrate later.
Yeah, I think they may try more. For example, their first level, second level, just as Xiaomi suggested, maybe the next time that just the third level, right? They can do a lot of experiment to verify it.
Yeah. Okay, so
Yuefan, do you have any question here?
No, thanks.
Okay.
No.
okay. So they have the paper has tried different pooling methods. For example, they have tried.
Oh, by the way, since it's ICML paper, do they have some proof or some other mathematical formulations in the paper? I think this idea is quite. I think this idea is clever indeed, but the intuition is Anyway, it's still straightforward. So I'm really curious that if we want to have an ICML paper in the future, what kind of writing it is supposed to be? Have a lot of proof there?
They don't have any proof. They only put some formulas to formulate the problem.
And maybe
yeah.
they can just calculate the complexity. So once they choosing different parameters and what is complexity. I think if I'm the one to write papers, the major paper writing part is how to calculate the complexity when we adopt different layers, for example, different levels and a different size of the sliding windows, and etc.
And their experiment is quite rich. They experiment.
Definitely. So but ICML, how long is the paper length? And what is paper length of the ICML?
Around
10 pages, including reference. You forgot it.
Yeah, probably.
Okay, let's proceed.
Sorry, may I ask another question? I'm confused here. For example, the output here is Q, right?
Where do you mean? Yeah, okay, yeah.
Actually, the output here is
it's embedding. I think it's supposed to be intermediate.
Actually, yes.
Right?
Actually, we can denote it as Y.
So the output here is Y.
Yes, it's Y, and
then what's the relation between Y and QI head?
I think QI head is derived from Y, right?
Y is used to go through a nonlinear projection, which is shown here.
Yeah, to generate Q tilde.
To generate QKV in the second level.
Then what's the Z here?
Z is the final output, right?
Yeah, it's the final output.
Final output.
Yeah, so basically they want to apply a nonlinear transformation from the embedding of from the input into the output. So this is basically to learn the intermediate representations of each token in the sentence. And Z is supposed to be, because the whole rectangle represents an encoder, right? Suppose that represents, the non-encoder is supposed to be represent a self-attention layer. And the input is actually the embedding of the sentence. And output is supposed to be another intermediate representation of a sentence. And then layer by layers, they try to learn such a transformation.
Okay, anyway, maybe I need to check.
Yeah.
But
anyway, it's good to know. This idea kind of interesting. But anyway, so it seems that ICML paper, it's good for us to know more about ICML paper. Maybe we need to then we can have a chance to submit it. Okay. Thanks, Yihao. Let's keep going on.
Okay. So for the pooling method, the paper has experimented with different settings. They have tried like max pooling, min pooling, and some
so they have very sophisticated comparisons.
Yeah.
Okay.
Yeah. And they also have a task-specific global attention settings. For example, when the model is going to tackle the problem of question answering task, then in this setting, because the question is usually short and compared to others, and the questions is all the tokens initials are quite important.
Sorry, I didn't get it. So maybe the voice is a little bit interrupted.
Okay.
You mean which one is shorter, the question or the answer?
Question is usually short.
Okay, the question is short, but it has a very long answer.
Yeah.
Okay.
For example, we have Q1. Sorry, Q2 2, Q3, and we will have A1 to AA. So they constructed for the problem setting like this. They constructed a goal set so that they put all the tokens the question in the question into the global set, so that for each token, when we calculate the attention for a token, the input, if it is not in the global set, then we will attend to string window.
Sorry, Yihao. So
I1.
is that my problem? I think your voice is a little interrupted. So it's not that consecutive. It's not that continuous.
Okay, maybe
Yeah,
my connection problem.
Yeah, so maybe let me. So your problem is that the question is short and answer is long. So they have a task-specific global attention. So they want to construct a global set, the Q1 to QL. For each token in such a set, the receptive field is the union of IW1 and G. And here I didn't understand the N notion. Would you please be more specific for that?
Yeah, this N notion is the sliding window of first level. It
Okay.
means so the I is means the I token, and W1 is the size of the sliding window of first level.
Okay.
So this means the range of first level sliding window, and it takes the union of the range of sliding window and the G. So for tokens that is not in the global set, which for tokens is in the answer for answer tokens, it will attend to the tokens in the sliding window plus the or it will attend to all the question tokens, and for the question tokens, it will attend to all the tokens in the sentence. So this.
Sorry. So will you please using annotations? I somehow still have a problem. Suppose they have. Let me start with that. Suppose we have questions and we have answers. Okay.
Yeah.
So by right, each questions corresponding to each answer, right?
Yeah.
Right. Suppose what for example, what's the size of NUS and what's the size of NTU? They definitely two different answers, right? Or what? And here it's a different question answers. And here it seems that we construct a global set to put all the questions together.
Not all the questions, because for each training example, it will only contain one question and one answer.
Yes.
So so here the Q1 up to QL means the
tokens in the queue. Okay, the token in the queue. Okay.
Yes.
And for each token, there is a unit G, and if the.
So the first line here means that for token that is not in the G, which means that
it's not in answer.
The answer
it's not in the questions, right? Not in questions.
For answer tokens, it will attend to the sliding windows and all the question tokens.
What do you mean by attended to?
And I mean, in the self-attention mechanism, the each token will attend to originally each token will attend to all the tokens in the sentence, right? In this paper, it will attend to the tokens in the sliding window. So here the change is that it will not only attend to the tokens in the sliding window, but also attend to all the tokens in the question, which is in the global set.
So your point is that it will add some additional link if the token is in the answer, right?
Yeah.
So for example, if I rewrite it, it means I is believed in
In
A,
answer.
in the answer,
Yeah.
right? So you will have additional, and then if it is in the
Question.
questions, and
Then
what
it
does
will
mean?
tend to all the tokens. It means all the
Okay.
tokens.
Attend to all the tokens. So is that means this token and here each I is a token in the question, am I right? Or
Yeah. Correct.
here I somehow get a big picture. So but I still have something I have to still have some confusion. So this token and this means that this token is inside the question.
Yes.
And
So
this
for this
means
QI, it will attend to all the tokens in the question and in the answer. But for this AI, it will only
no
attend
here the what are transformations? So it means that giving the questions and then we generate the answer. Right? So this is supposed to be a task.
no, the task is giving the question and the document answer. We want to choose a span in the answer that is the answer of the question. So
so maybe I think an example will help. For example, let's raise a question. What is the location of NUS? And what's supposed to be answer looks like? And what's supposed to be the document the task looks like? And suppose the question, yeah. It's supposed to be the task, right? So suppose the question is what is the location of NUS? And how do we convert answer?
Okay, so the document would be the input would be what is the location of NUS plus like NUS is the top rank university in Singapore and NUS is in Singapore. So there are some irrelevant sentence in the document, and the model is going to choose a span in the document that correctly answer the question.
Okay. So I got it. So this question answer is more like the choice question, right? So I think you may need to make the task a little specific. So given the questions and there are several answers, and the task is going to pick up the correct answer for the question. And here, so given this task, they will build additional self-attention layer. So that's more like a selective attention. If the one to naming this task is about a selective attention. Sometimes if we definitely know the relation between the question and answers, definitely we hard code how to build the attention there. Okay, so maybe we can ignore this detail and keep proceeding. I think we have spent enough time, and I think we grasped the general picture of the long. What's the name of the transformer? The long former.
Yeah, the Poolingformer.
It's a Poolingformer. Okay.
Yeah.
So it's good that if you can present the authors, because I'm really interested the other authors in the MSR, etc. Okay, please keep going.
Okay, so the complexity of this model is calculated as follows. So in the first level sliding window, because if the window size is Wn, then the computational complexity is all W1 and because the W1 we can choose it as a smaller as a small number and as a constant, so it can be simplified as On. And for the second level, we have the W2 as the sliding window size, and the
okay, so that's why it becomes linear. Okay.
Yeah.
But actually, I feel that it is more than definitely it's simpler than the On squared, but definitely it's more complicated than linear. But maybe.
But it's linear to the length of input.
Yeah, I think it's supposed to be 10 times linear, maybe 10. I'm not sure. Just a random guess.
Yeah, it depends on the sliding window size.
Yeah.
Actually.
And also the pooling size.
Yeah. Great. So this is the result of their experiments. So they have tested on the question answering data set, and the LA stands for long answer and SA stands for short answer. So you can see that it performs well on the long answer compared to other state-of-the-art models, and it's not the best on the short answer data sets.
Okay, so here,
as you can see here,
so the precision recall and F1 measure, right?
Yeah, correct.
And how do they calculate the F1 measure? So they're supposed to be, so they favor precision recall in F1 measure.
I'm not sure.
All right, okay.
And the first block here stands for the normal modeling, and the second block here stands for the those specialized modeling to tackle the long document. So here the models are designed to.
It seems like the long document is quite a trend, right? So
yeah.
So there's 4 papers published, but in within 2 years. Okay.
So before they tackle these long documents, they use different techniques, like split the document into different parts. Yeah, some of the papers use.
So this kind of occurs to me, maybe we can do something similar for the transformer. Okay, let's keep going.
Yeah, and this is another data set that have used on the summarization task. So the summarization task is to summarize the scientific papers on the archive, and
here with the abstract.
Yeah. Sorry, give me a second.
Okay.
Okay. So this one is the summarization task, and this 4K means they limit the input length to 4K, and this 16K is they limit the input length to 16K tokens, and it shows that the longer they take, the better the performance.
What is error? The Roger 1, Roger 2, and Roger error?
Is the Roger score is, I think it's calculated similar to blue score.
Okay, so it is just better than 2 points, or right? So compared to the baseline, it just improve 1 or 2 points. Oh, no wonder Dr. Gong say that 1 or 2 points is enough to perform publication because they do the same. Okay.
Sorry, what is the number 4K and 16K?
It's the length of input sentence. The maximum length of input sentence.
Yeah, so that means given the paper, you just pick up the top 4K and the second way pick up the top 16K.
Okay.
Okay. And they also did some ablation study to experiment different settings of the model. Like they have tried different number of sliding window size for first level and second level, and it's shown that the 128 for
on what
W1.
On what data set?
Sorry?
On what data set? What task is it? When they apply the ablation study?
Data set, you mean?
Yeah.
It's on the question answering dataset.
And what is LA and SA means?
LA means long answers, SA means short answers.
Okay.
And here C means the compression rate, which is the
second layer, the second level pooling size, or
yeah, it's the kernel size divided by stride size. So there is a very interesting conclusion here is that when we set the silent window size to be 515 and 12, you can see the performance is actually dropping. And they speculated that it's because when we put larger sliding window, it might be harder for the transformer to capture the relationships. So
that makes sense.
Yeah,
that's an interesting point. Okay.
Okay, and also they have tried different pooling methods, and also the layers of Poolingformers. Instead, they didn't apply all the layers to be two levels of to be the two levels mechanism that explained earlier.
Yeah, so here, just like Zhang mentioned, there's supposed to be 3 layers and even 6 layers, right?
Yeah,
and the 3 layers supposed to be the best.
Yeah.
Okay, so it's better for us to ask Yihao some questions. Maybe I ask the first one. If there's someone have a follow-up, that'll be great. So my question is about, so since this is about an NLP task, right? So before they still using the BERT for the wording gating, right? And giving the long sentence, there's supposed to be a limit for BERT model. Am I right?
Yeah.
And how do they address the length limitation for BERT?
They initialize the model with Roberta, and yeah.
And then the question comes to, there's supposed to be a limit for the size of Roberta.
Yes.
And how do they address this problem?
For the positional embedding, they just loop it.
Okay. Yeah, that is easy.
Yeah.
And how about the word embedding?
For word embedding, it's normal, right? Just each word is corresponding to a word embedding.
So I asked these questions for our own work, and how about the code BERT? Suppose we were have a long sentence or long method body. Suppose it actually consists of 2,000 tokens, and can code BERT handle this issue?
Yeah, I think yes. It's similar to the training process of this paper.
Okay, because here one of the ideas is that we need to learn a model to pick up the most relevant tokens and invite the most relevant tokens into the method body. So we may face a problem of long method body, and we pick up this paper presentation for this end. So, and also in my mind, I think giving code will have some relation, right? So if we apply the sliding window, we can additional calculate the AST relations or day flow and control flow relations to build additional attention mechanism, to build additional mechanisms for maybe you can learn a better model or better attention.
Yeah.
Okay, maybe you can take a point and maybe you can raise issues to Dr. and to have his opinion.
Okay.
Yeah. And yeah, is there any questions for Yihao's presentation? if no, let's think Yihao is really a very good presentations and well prepared. Since Yihao, and let's proceed to the next presentation, which will be
Thank you.
given by Ruofan. So Ruofan will give us presentations on detecting out of distribution images without learning from out of distribution data. Okay, Ruofan, please go on.
Okay. Mm.
If you find, you can just they are not necessary to make the full screens. As long as we can see the text, that will be okay.
Okay. There's something wrong with my computer. Oh, okay.
Hello, Ruofan, have you settled the issue? Hello, Ruofan. Okay, it seems this Ruofan seems to get disconnected. Hello, Ruofan. Okay, shall we start?
Oh, okay. So today I will present the paper Generalized Odin, detecting out of distribution image without learning from out of distribution data. And this paper is published in CVPR 2020. The first three authors are from Samsung Research, and the last author is an assistant professor from Georgia Tech.
So, so maybe you can introduce the authors a little bit. Okay, the first three authors are actually the researchers, right? So just industry researchers.
Yeah.
And the last author is assistant professor. Okay. So they work on the security. They also work on security issue, right? The second.
I think this means the security and privacy for neural network, not for web security. Yeah.
It doesn't mind. It's okay. Keep going. Keep going.
So the background here is when we train the network, we need a training set. For example, we train on the CVPR. But during test time, our model could meet any kind of data. If we train the model on CVPR but test on ImageNet, then it will not going to work because ImageNet has 1,000 classes, but CVPR only has 10 classes, and there are maybe also changing in data distribution, for example, changing in lighting condition, changing in background, etc. So the research problem is, how do we detect, given a model, then how do we detect whether a test data is in distribution or out of distribution? In distribution means it is close to the training distribution. Out of distribution means the distribution is different. Thus, we shall reject this out of distribution data.
Okay.
So a naive solution is the model may be uncertain on out of distribution data compared to the in distribution data. So we can build a simple classifier by thresholding on the max value of softmax probability prediction. For the in distribution data, we expect to have higher max value, but for the out of distribution, we expect to have a lower max value. However, the difference in top point probability may be subtle. If we look at the graph, if we look at the right-hand side graph, this graph is plotting the distribution of top one probability over many observations. And we can see that the green line denotes in distribution data. They are more concentrated towards 1, but the green line, which denotes out of distribution data, it is shifted a little bit leftward than the in distribution data. So you can see you cannot find the threshold to distinguish these two distributions.
So that is understandable. Okay, let's keep going on.
So inspired by this observation, researchers want to know whether is there any way to augment the subtle difference such that these two distributions become separable. In one of the state-of-the-art work, Odin, they propose 2 ways. The first one is temperature scaling. Second one is input pre-processing. So you can see after the 2 methods, 2 distributions become separable. Then we can draw a threshold here to separate the 2 distributions. The first solution is called temperature scaling. It is applied on the softmax. For normal softmax, this is the formula. After we add a temperature scaling, this is the softmax with temperature scaling. It had, because softmax is known to produce overconfident results, temperature scaling has the effect of spread the weights to other classes. For example, this graph is the distribution over category for the softmax probability. For an individual example, you can see that if we use the original softmax, then one probability get very high weights. But if we add the temperature, then the weights are spread to other classes, so it becomes more evenly distributed. Here I want to ask a question. What if we increase the temperature, then which figure we expect to have?
It's a very good question.
Or this figure?
Yeah, Ruofan, you can pick up the arbitrary students, audience. Yeah.
Maybe Yufan.
So Yufan is quite popular in these days. Hello, Yufan.
Sorry, I didn't get. Let me see. What if tau is larger? Original softmax if tau. Sorry, could you explain about the tau parameter?
Oh, tau is the temperature scaling parameter in here.
Max. Yeah, the tau is actually T here.
Mm.
Okay.
Maybe it's the blue one.
Blue.
So,
It's purple, right? The purple and yellow goes up and down, right?
I think maybe the down. I just
Okay. Maybe you can sorry, Ruofan, you can pick up multiple students and let them share.
then how about locus?
I'm not sure either, but I thought it was the yellow one.
Okay, so the answer is yellow one.
Congratulations to doctor.
Because if you let tau to be 1, then you goes back to the original softmax. So this is tau equal to 1, this is tau equal to 2. So if tau becomes larger, if tau is sufficiently large, then you expect almost uniform distribution over all classes.
So a straightforward idea is that Ruofan, you please go to the previous slide. So suppose tau is very large, it means that D is supposed to be 0, right? Right, and E0 is supposed to be 1. So every point is supposed to be every population is supposed to be n. So that it will be n with uniform distribution.
Yeah.
Right.
Mm.
So this is basic idea to take the extreme. Since this tau is supposed to be the monotonic. So suppose the T is very small, and there is supposed to be a very large. And there's supposed to be an entry supposed to be have a very large value, which squeeze the other options. So basically, the larger the T is, the larger the entropy, and vice versa.
Yeah. So the temperature scaling trick has been used in confidence calibration to reduce the overconfident prediction produced by softmax. But in Odin, they find that temperature scaling has the ability to separate the in-distribution data and out-of-distribution data. After temperature scaling, the out-of-distribution data maximum softmax score concentrate more towards 1 over n. So here, the gray curve is the out-of-distribution data. They concentrate more towards 1 over n. But for the in-distribution data, it is slightly more robust to temperature scaling. Their maximum probability is a little bit higher than the gray curve. So there's a trend that these two distributions can become separated, but there's still a large non-negligible overlapping area. Thus, we can still not use a threshold to separate these two distributions.
I have a question here. So is it like an empirical result, or do they have theoretical proof for this phenomenon? Like the out of distribution data after temperature scaling would concentrate it towards 1 over n. Hello?
I think it's just as Dr. Lin has explained. T goes really large, then this ratio will become 1 over n.
No, I mean in
Odin paper.
Yeah, do they have mathematical proof, or they just say that they do experiment and this is the result?
I think they have mathematical proof to interpret this separation.
But these data are supposed to be the real data, right? And I think there is a distribution, or they just just draw the distributions based on their imaginations, or.
This is not from the original paper. So in the
Okay.
original paper, they didn't draw this. They do have some proof, but I think the proof is not that formal or strict. It is just for some interpretation.
Okay.
So I think maybe it's more empirical results than theoretical results.
Okay.
So because it is still not distinguishable, so ODM proposed the second solution called input preprocessing. After the temperature scaling, we can get the softmax probability, and then we take the maximum of it. That will be the maximum calibrated probability. And then we preprocess the input by adding the perturbation on X, and X becomes X tilde. Then we feed the perturbed input X tilde into the network again and compute the maximum probability and threshold on it. So if we take a closer look at this input preprocessing method, it looks like the adversarial example generation. But in adversarial example generation, the focus is we want to add a small perturbation on the input such that it can decrease the softmax score for the true label and force the neural network to make a wrong prediction. But here in odin, our goal is the opposite. We want to increase the softmax score of any given input for the predicted class. It turns out that the perturbation can have stronger effect on the in-distribution data than out-of-distribution data. So that makes them more separable.
So here, maybe I lost a bit. So can you clarify it more that we aim to increase the softmax score, increase the softmax score? So I assume that's supposed to be the, please put up.
Because this score is the maximum calibrated probability, which is just the probability from, which is just the output from neural network.
That means that if we apply the temperature, there, maybe increase the temperature. Suppose we increase the temperature, we want to find whether there's still a mutation to improve the softmax score.
Oh yeah. So here we further improve the softmax score.
So that means for the auto-distribution samples, it is harder for us to find such a perturbation.
Right? Yeah. So here you can look at the visual interpretation, maybe it's clearer. X1 is the input in distribution image. X2 is an out of distribution image. So if you take the same step size, then compared to X2, X1 can increase more in its softmax score because your data is trained on in distribution. So it's more sensitive to perturbation. So that's
why. There is a hypothesis, right? So that is supposed to be a hypothesis. Okay.
So that can widen the gap. That can widen the gap between in distribution and out of distribution.
Any question there?
Okay, Ruofan. In this, please say the slide 13. My understanding is that intuitively, the temperature scaling is to concentrate those peaks in the softmax value in this plane, right? To concentrate those peaks to let the activation value to be easier to separate. And my understanding of the pre-processing is we first do a step of like a gradient descent to make the points, the tilde x to be more closer to its target, right? So the in-distribution data and out of distribution data can be more easily to be distinguished. Is my understanding right?
Yeah. So it's something like you take a step of gradient descent.
Okay.
Okay, good question.
And this paper is called Generalized Odin, so it's built upon Odin. They argue that in Odin, because you have a temperature scaling hyperparameter T and a step size in input preprocessing epsilon, they need to be chosen by a out of distribution validation set. But what if we don't want to have out of distribution validation set? We just want to tune based on in distribution validation set. And also the intuition in Odin is that they want to they define that Sx, which is the maximum probability after temperature scaling, is correlates to the domain posterior probability, PD in given X. So this means the probability that X is from the input distribution. And then we threshold on Sx to classify whether it's in distribution or out of distribution. So is it possible to directly learn this in distribution probability instead of we find an Sx that is correlate with this probability and threshold on Sx?
So here, would you please more specify by the D value out, the D value out? The D value out, yeah.
This means the out of distribution validation data set. The capital D denotes a data set.
Do you mean that they try to find the threshold without any out of distribution data? Or
yeah, they try to choose the parameter without any out of distribution.
Yeah, and given the paper, they're saying that they do not need such a data set, right?
Yeah.
Because they're saying that they want to learn out of distribution data without any. They want to learn out of distribution samples without looking at any out of distribution data.
They actually want to search this best hyperparameter.
But if they want you, since you mentioned search, so do they prepare some data set during training? Or anyway, they need to
they only need in distribution validation set. They don't need out of distribution validation set.
Okay.
Keep going on. The contribution of this paper is they provide a new perspective of decomposing the confidence into two parts and directly modeling this our interested conditional probability here. Second contribution is they modify the input preprocessing method without the need of tuning on out of distribution data. Third contribution is they do comprehensive experiments under the setting of learning without out of distribution data.
Okay, so let me recap. Okay, so this is also the question I want to ask. So the X, the probability of Y and the D in giving X and the P D in giving X. Okay, maybe you can keep going to be more specific on your points.
So consider we have a classification network which makes prediction of probability of Y given X. So this is given an input. We produce a probability vector, for it belongs to different classes. Since the network is only trained on in distribution, so there is actually an implicit condition that the prediction is made based on in distribution set. So actually, py given x is equal to py given d in and x. That means x belongs to the in distribution.
Okay, keep going on. So the base comes, right?
Then we apply the base rule. For the first equation is we just directly apply base rule. And the second equation is we apply chain rule. And we observe that px appears in both numerator and denominator, so we can cancel it out. Then we can write it like this. So in this way, we decompose the output prediction into these two parts. And note that this conditional probability is just what we want to get.
So we just need to change the formula, right?
Yeah, but
So can you interpret a little bit about this probability? So this is given x, the probability of.
for example, this is the probability of y equal to some class I. Then this will become given an x, what is the probability that it belongs to in distribution data, and also
Falls in the category of I.
its class is I. The denominator is without considering the
And
class.
the event of D in means that X belongs to in distribution data.
Yeah.
Okay.
However, there's no explicit way to decompose it into these two parts, but we can force the network prediction to have this kind of divisor structure and hope that it can learn the decomposition automatically. This is the largest output from the network. Then we will grow two branches. We let one branch to learn hx and second branch to learn gx. Then we let the final output to be hx divided by gx. That's here what I mentioned. We force the network to have a divisor structure. And ideally, we think that hx will behave similar to this numerator here, and jx will behave similar to the denominator. Yeah.
Here. Okay, please, Chang, please.
Okay, Ruofan. Could you give more details of the motivation we designed the HX and GX, and what are the intuitions of the design of HX and GX?
Because we want to directly learn this
Probability, the probability of X belong to probability of D in given X, right?
If we know it, then it is automatically out of distribution detector, right? We can just threshold on this probability.
Yeah, I think my understanding is that the probability of D in and X is given a sample X, the probability of is in distribution data, and that's and that's what we want to know, right?
Yeah, that's correct.
And we design the divisor structure to implicitly
To learn such a probability.
to introduce the D in to the softmax structure, right?
Yeah.
Okay.
So somehow looks smart until now, right?
Yeah, but I feel it is not clear because the story is good, but how do you make sure that this GX really learns the conditional probability we want to get?
Yeah, I understand. It means that only just conform such a form does not necessarily means GX equals to P in giving X, right? So that's your point. But it's just the form because but as long as it controls the GX always within 0 and 1, Now, what if we always control the GX always between 0 and 1?
Yeah,
And G and HI always within 0 and 1. They're supposed to be.
I know you mentioned that one of their contribution is they want to do it without the out of distribution data, but I think if they can like introduce the out of distribution data and label them when training the model and then label the PD in to be 0, then maybe
Easier. It's easier.
yeah,
For the final
it's
test.
easier, but
Yeah.
it's more explainable, right?
Yeah, I think one of the issues to introducing an additional auto-distribution data is that actually it's the number of types of auto-distribution data is actually infinite,
yeah,
right? So
Yeah.
basically, the problem is that what is and how much auto-distribution data we need to look into, and whether the auto-distribution data can be generalized to the other kinds of auto-distribution data, right? So that's basically the question we may ask. But anyway, let's focus on Ruofan's presentation and see how the authors design an architecture.
Okay, so as I mentioned, the network has 2 branches. So from the second last layer, I grow 2 branches. One is responsible for learning HX. The other one is responsible for learning JX. For JX, it is a fully connected layer followed by a batch normalization, followed by a sigmoid activation. So they will control JX to be
0 and 1, right?
yeah. And for HX, they have 3 ways of designing HX, which I don't really understand why they design it this way. And they
Please
didn't.
go on. So, but it seems that HX cannot guarantee it will be normalized into 0 and 1, right?
Oh, yeah. So here the question
Okay.
is a simple one. So maybe I just answer it.
Maybe not, no, you can just cut the questions. Maybe let more people involved.
Maybe Yuchen.
I actually have no idea.
So just no, that's just pure maths. You can just start with the second and the third formula. So just calculate the range of the y given x and what's the range of y. So maybe you can have try with the second one. Definitely it's smaller than 0, right?
Transpose. So is the last one some cosine? It's like a cosine, right? So it's between -1 and 1. So that's HC.
Yeah.
Yeah, that's correct. Yeah.
That's,
Yeah, maybe leave the other equation to the audience.
I think you just answered it, right? You just answered the second one.
Okay.
So the second one is smaller than or equal to 0. Third one is between -1 and 1. First equation can be any real number.
Okay. So good answer and good question.
So because this fx is not controlled within some range, so they need another softmax layer after fx to produce the prediction. Then we let the sx, which is the scoring function, to be jx. Remember that gx can be seen as the proxy of this conditional probability.
Just another contribution.
What is HI? Is it the sum of the three?
Oh, they have tried 3 ways.
Oh, I see.
One of it, yeah.
Okay.
I think they're supposed, when we design a model with that, with at least within the structure, right? A structure like make sure the GX belongs to 0 and 1, HI belongs to 0 and 1, and the HI over G will still between 0 and 1, right? At least we need to make sure have these hard constraints on the model.
But they didn't constrain H.
They suppose if H is corresponding to a probability.
Because this is the largest. After that, you have another layer of softmax. So you
I understand there is another one, but if we added a software, if we added let me think about it. So
Why don't they apply the softmax after HI and then divide it by GX?
HFI.
I think it's because they want to apply softmax for this whole divisor, not for the numerator itself. Because the softmax is for this probability, not for this conditional probability.
Okay. So the only rationale is that if they form such a division form, and the GX supposed to be the probability of X pointing to the in distribution.
Yeah.
Okay.
So we let the scoring function to be GX. And then we use the input pre-processing method just as odin, but here the SX is JX. So we will perturb input to increase SX, which is to increase the probability that this input is from in distribution set. Okay. And the step size epsilon is chosen, which can maximize the SX of the in distribution validation set. So there's no need for out of distribution validation set.
Okay, keep going. So I still doubt the rationale of this book sample. This is the in distribution transformations. Of course, given in distribution, it will have it may have giving a small learning steps epsilon, it will reach a high probabilities. But it cannot guarantee in the out-distribution space. There are also a peak in the out-distribution examples, right? And given an epsilon, it may also reach a very high. Just saying that this rationale may not be 100% guaranteed. Right.
I think the idea is that like if we have a in distribution point in here and out of distribution learned out of distribution data here, and now we are at this point and this point, we can see because the activation value is both relatively low in the in distribution and out of distribution data. So in this situation, if we can do a step of like a gradient descent, or this other say the pre-processing, we can step forward to the center, just in the local optima. So
Yeah, my point is that this is a shape you read, this is a shape you draw from the imagination. It is also possible that there's a multiple peak there. Another peak may not here, right? There's multiple peak here. And this is outer distribution peak. So if we start with another samples, it may reach a very high. It may not reach that high. So because the search space is really complicated, it's really hard to say.
Yeah.
But I just mentioned that it may not guarantee.
Yeah.
Maybe empirically, yes, but not theoretically guaranteed for such a solution.
Yeah. So I think the pre-processing idea is to amplify the differences between the in-distribution and out-of-distribution data. We take an extreme example, like if we first add those places, both this is in-distribution data and out-of-distribution data, we can see the activation value are both very low. So we cannot distinguish those 2 points good. But if we can move them to their own local optimal, we can get a obviously difference between them. I think this is the idea, right?
Yeah.
Okay. Yeah. Good clarification. Let's keep going on.
So this is the overall solution for generalized OD. So first we calculate the scoring function, which is equal to the output from the GX branch. And then we do input pre-processing. After that, we feed the perturbed input and compute the scoring function again. And by applying threshold on it, we can build a classifier for in distribution data versus out of distribution data. So this is the experiment they do. They have.
By the way, so do you have a small question here? So giving GX, would you please go back to the previous slide? So giving this GX, the GX is actually just equal to P D in given X, right? So so why not just using GX, and we need to still need to apply this pre-processing stuff?
Because as Changsheng mentioned, they want to amplify the difference. So we still use the input pre-processing.
I think the logical is not that smooth for me. Since once they design a branch which is GX, another branch is called FXI, right? And the final output is supposed to be so this is H. Sorry, the final output is HI divided by GX, right? Anyway, so this is not 100% accurate, but anyway, so that is computation graph, right? So once we got that, and the idea of this pre-processing is just used for softmax. And here
can be used for any scoring function. Right. SX can be, yeah. SX can be anything.
And here the GX is computed by the sigmoid function, right? If I remember correctly.
Yeah.
So here the GX, okay, maybe it's okay.
May I ask a question here? How can we learn HX and GX? When they learn them simultaneously or separately?
Simultaneously, supposed to.
Yeah.
Maybe you can go back, Ruofan, we can go back to the.
So, yeah. Actually, here you completely change your original network structure. Now you have 2 branches and you learn it together. The latter part I didn't draw. The latter part is just I combine these 2 branches by
divided.
And then apply a softmax, and then you can compute the loss as usual, then back propagate it.
Okay, thank you.
So here you have a 3 in distribution data sets, and also we keep some out of distribution data sets. They also include the uniform random images as well as Gaussian random images inside the out of distribution data set. And they have used 3 networks. The evaluation metric is the area under ROC curve. Because the OD detector is a classifier, so you can draw the ROC and compute the area under it. Second evaluation metric is the true negative rate at 95% recall.
Okay.
We have in total 3 baselines. The first one is just thresholding on the original top 1 probability. Second baseline is odin. Third baseline is called Mahalanobis distance. So the idea is we take the intermediate representation FLX. This represents the output features at the Lth layer of neural networks. And then we compute its distance to the training data. We estimate the mu I, sigma I. The mu I and sigma I here are the class mean representation and the covariance matrix for the training data. And then we compute the distance.
And is that a threshold there?
Yeah. And then we use a threshold to distinguish those out of distribution and in distribution data. When the distance is high, then we think this data may not come from the same distribution.
Okay.
So here I have a question is, why do you think Mahalanobis distance is better than the Euclidean distance? This is the formula for Mahalanobis, and this is the formula for Euclidean distance or L2 distance. Maybe Changsheng, can you answer this question?
Okay. So my understanding is that if we use Euclidean distance, we didn't consider the difference between the difference of the metrics, right?
The difference of the metrics.
Of the like if we want to calculate like a distribution of body heights and another distribution of body weights. These are 2 distributions, but their meaning and metrics are different. One is in kilograms, one is in meters, and their their contexts are different. So if we use the Mahalanobis distance, we can unify can normalize the different scales between dimensions. Is that right?
Yeah, that's right. That's one of the reasons. Because I think what you mean is Euclidean distance is not scale invariant. When you have different dimensions and different dimensions have different scale, they have different variance, then this is not properly normalized. But because the Mahalanobis distance has this normalization on variance, so it's automatically scale invariant.
So can I see the formula of Mahalanobis, the formula of Mahalanobis distance again?
This.
And what's the sigma minus? This is divided by sigma.
This is the covariance matrix of your high dimensional vector.
So is that okay to move this item backward?
Cannot.
Cannot.
This,
Why?
this matrix multiplication.
This is matrix multiplication.
Let me check. So how do you expand this formula?
Oh.
The previous slide. Can I see the previous slide?
This is the same as this, right? This is the same as this.
Yeah, so I'm not that familiar with this formula. Yeah.
Your mu is the column vector, right? Maybe it's of dimension d times 1. And d means you have multiple dimensions, for example, multiple neurons in the same layer. And fx is of the same dimension. Right.
So fx and mu are
So here I'm talking about a general fx and mu, not restricted to the context here when we're talking about neural network. Here is a general mu and fx. But here you take the transpose. So the whole thing becomes 1 times d. So it becomes a row vector. And this is the covariance matrix, which is of shape d times d. If you expand this covariance matrix, then it's like this. First of all, the diagonal entries are the variance. For different dimensions. And the off-diagonal entries are the covariance between different dimensions.
do they need to be square? No need, right?
No need. And then you take the inverse of this covariance matrix. But when you take inverse, it doesn't change the shape of, it doesn't change this shape d by d. And again, this term is of shape d times 1. So if you multiply these 3 components together, you get a 1 by 1 scalar, which is the distance.
So let me think the covariance. I think of the memory is a little fitting about the covariance. The covariance
is actually proportional to the correlation. So you can imagine it's some kind of normalized version of correlation, because usually you don't expect, because the independence assumption between different dimensions might be a too strong assumption. So that's why you need this covariance matrix to model the correlation between different dimensions.
Okay, a good explanation.
So actually you couldn't.
Sorry, can I ask a question in page 27? What's the I mean here? It's a class?
Oh, it's a
class level. So it makes I mean the equation 2 is the
it takes the closest distance.
When it will have the corresponding label. Close the distance.
So, by the way, we do not know the label of X, right? All right. So we just choosing given I choosing the
yeah, we just choose
the max or minimum. The max or minimum. Oh, because it's negative.
Maximum minus, so it's closest.
Yeah, so, I mean it's for example, there are 10 classes. They choose the that means there have 10 mu. Then they will choose. So then it will have the classification.
Yeah, they will also have the classification. They will indicate which category there. But yeah, I just feel that it's also possible that each class may have multiple mu. Right. It is still possible.
Each class only have 1 mu. They just collect all the training data belongs to that class. And
I understand. What is suppose there's maybe
Oh,
binary classifications. And,
multi-model distribution. This kind of,
yeah. So
they just simply assume they like
the distribution is the same, right? There's just one Gaussian distribution. There's only one peak, but it is also possible they have several peaks here. It means that we may have several mu there.
yeah. So because Euclidean distance can be viewed as a special case for Mahalanobis distance, where the covariance matrix is simply equal to identity matrix. But if it is identity, then the implicit assumption is that the dimensions are independent from each other, which may not be the case for the neurons in the same layer because they might be correlated. Second reason is what Changshen answered is the Euclidean distance is not normalized by its variance, but the Mahalanobis distance automatically normalized, so it's scale invariant.
Okay, that's a very good question here. Even I learned something from these questions. Okay, keep going on.
So here is the experiment result. We can see, this is the, for example, this is the in-distribution data, and they train the model on it and test it on these rows of out of distribution data, and they calculate the area under ROC and the true negative rate at true positive rate of 95%. The last column is generalized odin, and the first three columns are the tree baseline I just introduced. We can see that in most of the cases, the generalized odin outperforms the rest. But we can say for the case of uniform random images and Gaussian random images, Mahalanobis distance performs very well. Yeah.
Could you please explain the TNR, I mean true negative rate?
Oh.
No, I mean here, because I feel it seems the results is not that good. I mean, in this specific one. So that means 95% in distribution, but for example, if we detect 95% in distribution, then we can detect the 87, maybe 90% of auto distribution. Is that correct?
Yeah.
So yeah, that means, for example, we have 5% in distribution is misclassified. But actually we can only detect 90% of OOD. So I just feel the results of the TNR actually is not that good, right?
Because you didn't look at any out of distribution data, so I think the performance might be acceptable. Yeah.
Okay, thank you.
So I noticed that they have one interesting experiment is that they distinguish two types of out of distribution. The first type is called semantic shift. It is when the model meets new classes that didn't appear in the training set. Second type of distribution change is non-semantic shift. Is here when it changed from real image to sketch image to infograph to quick draw, this kind of thing. Well,
how do they go to quick draw or search from the internet?
I don't know.
Okay.
Maybe there's yeah.
This is the domain net data set.
Oh.
Okay. Okay, let's keep going on. I think for the quick draw, it's very difficult, right? Supposed to be.
Actually, they find that semantic shift turns out to be the hardest one to detect. So non-semantic shift seems to be okay. if the dataset has both types, that means it's both semantic shift and non-semantic shift. Then these are easier to detect.
So let me look at the quick the quick draw.
This row, yeah, this row is semantic shift. Means you have some new characters, then it is actually not better than the simple baseline, which is thresholding on softmax. But for the rest kind of scenarios, then generalized odin, that's the best.
But for the sketch pane, the okay, keep going. So the value is still quite low, right? You can see here.
But the baselines are even lower.
Okay. Okay, keep going.
So the takeaway here is the three contributions of this paper. First one is it tries to decompose the confidence into two parts and directly model probability that X is from in-distribution data. Second thing, when they do input pre-processing, it does not rely on any out-of-distribution validation set. And third thing, they do some comprehensive analysis with experiments under this setting without out-of-distribution data.
I feel that is an interesting papers, especially when they decompose the confidence into two components. So, Ruofan, so my question is from your point of view, do you think that there's any problems or what do you think about this approach?
I think the I just feel confused about here. How do we explicitly draw the relation between HX to this and JX to this? And it is impossible to verify that JX really approximate this probability well. So.
And from the experiment, and it's showing that the GX can work somehow well in some data set. Can I look at the experiment data? Okay. Okay. Since it's already 5 p.m., maybe we need to call it days. But anyway, Ruofan make a very good presentations and also prepare very good questions. Okay, so is there any questions for today's presentation? Okay, if not, Ruofan and Yihao, please share your slides. I think Ruofan has already shared. And then I will actually publish our videos in the YouTube and share the links later. Okay, thanks everyone. Bye.